Okay, moving into the last little bit of chapter 2, we're into something called kinematics, which is a description of how things move. So this is maybe the quote-unquote physics that you were thinking of when you signed up for this course. Here's what we're going to do. For these kinematics problems, they're going to be word problems where we pick from a series of equations. I always want you to make this list of variables with every question. So it's not a make work project. It will help us get organized, I promise. There are 5 variables that we are going to look at with these problems. VI is the initial velocity. VF is the final velocity. Those units have to be meters per second. So watch that they're not in kilometers per hour. You might have to do a conversion. There's a D for displacement in meters. A is acceleration, meters per second squared. And T is your time measured in seconds. So I like to call this little list here the VIF-DAT list. VIF is the VI, VF, and then DAT, DAT. And I'm an old dog. I can't learn any more new tricks. Ask my wife. I have been trained to always do them in that order, so I will continue to always do them in that order. Doesn't really matter, but if we all stick with the same order, it's kind of nice. So VI, VF, DAT. Now, what's going to happen is you're going to get a formula sheet soon, sitting online if you want to grab one right now. And those different variables don't all show up in the equations that we've got to choose from. In fact, you pick equations based on which of those 5 variables is not given to you in the question. So here's what the equations look like. If you are not given a displacement in a question, and that's not the thing you're trying to find, then here's the equation that's going to work really well for you. VF equals VI plus A times T. You don't have to memorize these equations because they're on the formula sheet. You just have to know how to use them and when to use them. Now, what if you're not given a final velocity, nor are you asked to find a final velocity? So this doesn't mean the thing doesn't have final velocity, the object. It just means we don't know it and we weren't given the final velocity. Well, there's your equation. D equals VIT plus 1/2 AT squared. Again, it looks confusing, but it's not. Really what we're going to do is the 1/2 is just going to turn into a 0.5 in our calculator when we go to plug it in. Easy stuff. What about if we've forgotten a stopwatch for an experiment? So we don't know what the time is. We're not asked to find it. You can actually use, this is the same equation here. You can use either version. You'll notice that the version on the right-hand side, we simply took the negative VI squared and moved it over. It turns out this is the version that a lot of students like to use in Physics 11. This is the version that you typically see on a formula sheet. I've given you both for this year, so I would probably suggest leaving things positive. Life's a bit easier. Now, what about if there's no acceleration? Again, the thing could be accelerating. We just don't know what the rate of acceleration is. Well, you can use that equation. And some of you might be writing that down going, hey, adding 2 velocities and dividing by 2, that's really just an average velocity. And you're exactly right. So there's another equation you could pick from if you're ever asked to just find average velocity. VI plus VF divide by 2. Some people call it V bar. A little bar over top. So that list of variables is going to help you stay organized and pick the right equation. In these equations, just so you know, you would be responsible to run the algebra to solve for any of the variables in the equation, not necessarily just the one that's isolated. You got to run the algebra to find whichever one we might need. Okay. So let's take those equations and apply them to some word problems. Again, feel free always. Read this word problem, but don't write it down word for word necessarily. You can shorten it up for yourself if you want. We've got a car initially going 14 meters per second. Maybe it's going to pass somebody and it accelerates at 3.50 meters per second squared for 120 meters. Find VF. How fast is it going at the end? So we always want to make this little list, the VIF-DAT list, to help keep us organized. When we go to put values in this list, I'm not worried about sig figs, I'm not worried about units, just trying to get the numbers matched up with the correct variables. That's it. So here's where they go. In fact, here, I wouldn't even put 14.0, I would just put 14. And for an acceleration, I wouldn't put 3.50, I just put 3.5. But we've got an initial velocity of 14. Final velocity is what we're looking for. Displacement was 120 meters. Acceleration's an easy one to find because it's got those crazy units, 3.5 meters per second squared. And you'll notice at no point does this question give us the time or ask us to find the time. So that's the variable that gets axed out. One of them always gets crossed out. And then we go back to our equations and we pick the one that doesn't have time. I'd probably go with this version right here. Oh, I lie. I picked the other one. Sorry. Old notes. Plug the numbers in. Once you've picked the right equation, that's kind of the tricky part. Now it's just some calculator work. There's your answer. Again, hopefully you're not getting stuck with the algebra. If so, get in touch with me and we can go over it. But really, we plug the numbers in. Plug in your VI, your A, your D. Going to throw this half into your calculator. Add 14 squared to both sides. We get 1036. That's VF squared. And then you take the square root. We want final answers to 2 or 3 sig figs. You should get 32.2 meters per second. There's your final velocity. Let's try another one. Again, don't feel like you need to write all this down word for word. Person throws a rock straight up into the air with an initial speed of 12.5 meters per second. Find the rock's displacement. Pardon my grammar. And we're talking about like an actual rock, not Dwayne Johnson. Ha ha ha. Find the rock's displacement and velocity after 2 seconds. It's actually asking us to find 2 different things, which means we're going to have to use 2 different equations. You can't use one equation to find 2 unknowns. It doesn't quite work that way. Now, in this case, there is a number that we have to kind of know is going to be true. Here we have an object. I'm going to say that this rock is falling down, even though you're throwing it up into the air. Or maybe you could call it falling up and then falling down. Any object in the absence of air friction, whether you throw it into the air or just drop it, it's going to accelerate downwards because of gravity. And gravity always pulls things down, again, ignoring air resistance, at negative 9.8 meters per second squared. The negative is very important because it's down, so you have to catch that. It is very common in these word problems to not be given that number. You have to know that number. So whether you throw a rock or a piano or Dwayne Johnson, the rock, into the air, as soon as it is free falling, as soon as it's in the air and unsupported, gravity is going to pull down negative 9.8 meters per second squared. And sometimes students will say, but Heinrich, the thing is still going up. Yeah, but it's eventually going to come back down, right? So it's going up, but it's slowing down, and that's because gravity's pulling down at that 10-ish meters per second squared. So we'll make our list of variables. We'll get ourselves organized. Left the person's hand at 12.5 meters per second. There's actually 2 things we're looking for. We do have to look for, like I said, just one at a time. So maybe we'll find displacement first, in which case I would actually do this. I'd say I know the initial velocity. I'm trying to get the final velocity. I know acceleration's negative 9.8, and I know that we're looking for 2 seconds. So I'd actually cross out the D, go pick yourself an equation, which is going to be this one, which looks kind of scary, but it's not. You got to trust me on that. Plug the numbers in. The fraction's just going to turn into a 0.5. Looks like that. I show 2 different numbers here, but in fact, you know what I would do? I would suggest that you don't even show this step. To be perfectly honest, I would just plug this into your calculator in one step. Let's try it out. Hopefully you can see all this. This is what I would do. One shot. You don't need any special brackets. It'll work out nicely. 12.5 times 2 plus 0.5 times negative 9.8 times 2 squared. Again, no brackets. The bed mass, it's going to do the multiplication first, which is what we want. Boom. There it is, 5.4 meters. So I'd actually go straight to the answer there. 5.4 meters. So that is your displacement. Now, when we go to find the final velocity, sorry, we'd scratch that one out, I think. When we go to find the final velocity, we probably don't want to use the 5.4 meters, just on the off chance that we kind of screwed that one up. So here's what I would do. I'd actually make a second list where I just use the information that the question gave me. And this time I have final velocity as my question mark and displacement is out. So we need to find an equation that doesn't have a d. Hit your formula sheet. There it is. Probably the easiest of all. VF equals VI plus AT. You go and you plug your numbers in there. Again, one-shot deal on your calculator. Don't do it in 2 steps. You get negative 7.1 meters per second. So 2 or 3 sig figs, got it. Units, got it. Beautiful. Not too bad. Oh, and I was thinking about this while I was going. I can't edit this video, so I'm just going to apologize. I'm sorry. I initially did this. Where was it? Right there, we scratched out D, but I actually went and then solved for displacement first. So pardon me, let's rewind the video. This is what our first kinematics list should have looked like. Sorry, you probably caught that way before I did. I'm slow on the uptake. I apologize. Silly me. It's okay, nobody got hurt. All right, last example for this lesson. Again, don't copy this word for word. See if you can trim it down somehow. Here a ball is thrown straight upwards and it takes 5.2 seconds to get back to the ground. Find the maximum height. I would start with the kinematics list. As always, I'm going to do this one with you so I don't screw things up. Now, kind of crazy, they're only giving us one number in the question. They only give us 5.2 seconds. And some of you are going to go, yeah, but we're throwing something up into the air, so it's kind of like falling up. It's eventually going to fall back down. We know acceleration then is gravity. You're exactly right, negative 9.8. Maximum height, what are we looking for? Well, a height is like a displacement. How far does it end up above the ground? And now we're kind of stuck. Like, we got to figure out one more value here, and we don't have it. And I'm actually going to scroll back in the notes here for a second and point out something that I don't know if you noticed. Looking at those 5 variables, turns out one of them is more important than the others. Look at the red here. You can work with no D, no VF, no T, and no A. But you have to have an initial velocity. It's the most important of the 5 variables. You either need to know it or you need to be finding it. But at no point can you ever make your VFDAT list and then put an X beside the initial velocity. It just doesn't work. There's no equation that'll work with that. So what we're going to have to do is somehow figure out, how do we get an initial velocity when the question doesn't tell us how fast the thing was moving when it left the person's hand? And that would have to be the velocity, right? If you thought about it being thrown into the air. It's not 0. It would be the speed it had when it left the person's hand. Now, what we need to do then is think about an object going up and going down. So what an object does when you throw it up into the air is it goes up, 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 up. What does it do? It's slowing down. And what does it do right at the very top at maximum height? So at maximum height, which is right there, oh, kind of crazy. The thing, for just like a fraction of a second, it stops, and then it starts picking up speed and actually falling down. So it falls up, 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 stops, and falls down, 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 down. So what we're going to do is we're going to think about sort of looking at it and saying, well, if it stops at the top, can we just think about the trip downwards? So let's look at just the fall. Let's not think about throwing it upwards from the ground. Let's think about it falling from maximum height. And if we look at the fall, then we can say, hey, cool. That initial velocity is 0. 0 meters per second. Although we have to be a little bit cautious here, because if we're looking at the fall, then we're only looking at half the trip. We've ignored the first half, the falling up. And that means we actually have to take the time and we have to cut it in half. So we need to use only half of your total time. And some of you might go, whoa, whoa, whoa. Does it actually spend half of its time going up and half of its time going down? The answer is yeah. The reason you can actually split the time right in half for up versus down is because gravity's locked in at negative 9.8. So as long as it's slowing down at the same rate that it starts speeding up on the trip down, we can simply chop that time in half, 2.6 seconds. So we don't need a final velocity. We can go and pick an equation that doesn't have a VF. D equals VIT plus 1/2 AT squared. Actually a really nice equation to use in this case, because that initial velocity at 0 means this VIT portion of the equation, gone. I'm actually going to scratch it out so that I don't make the mistake thinking that 0 multiplied by 2.6 is a number, because it's not, it's just 0. So if we go and we solve for D, I'm going to scroll into my notes here at some point. 1/2 times negative 9.8 times 2.6 squared. Let's just do it on the calculator. It doesn't take us long. Half times negative 9.8 times 2.6 squared. Negative 33.1. Meters. 2 to 3 sig figs plus units. Now some of you might be picky and you might say, well, that's not really a height if it's negative. I get it, right? So it's negative 33.1 meters is what the math told us because we looked at the fall. We actually told the math to do that, so it spit out a negative. I'm okay with you having a final answer that's a negative, but if you look at that and you're like, no, Heinrich, I'm picky. The maximum height should be measured from the ground up, positive 33.1 meters. I'll take that too. Really, either of them works. So there's your last example for this first round of kinematics. The homework that goes with this is worksheet number 5, numbers 1 through 9. And I would highly suggest that you try some of those out before watching the next video, because we're going to ramp things up a little bit in terms of difficulty level with the kinematics. Not that it's going to be super hard, don't worry, but challenging is good. But it certainly does get a little more challenging. So try numbers 1 through 9, get the basics down, and that way you'll be ready for me to up the ante with the next video.